Cuteness is a kind of beauty belonging to things which are attempting to become something that they're not yet capable of being. For example, young animals or children trying to act like big and tough adults. Along these lines, we find that the emblematic carriers of today's cuteness are anime girls. And with cuteness, we may find that the more is the merrier. So why not create an infinite flood of anime faces? Well, that's what we'll do in this video by making use of StyleGAN2 and a pre-trained anime face data model. It's more of a how-to video, not going too much in depth into the machine learning element of it, but more a step-by-step exploration of what we can do to generate new faces from a pre-trained model and then save those down, so we've got them somewhere. I also wanted to go a step further and create a basic web app prototype so we can share these faces to our friends or online, more externally. We'll be using Google's Colab cloud service, where we can just code in Python online with access to a GPU. So let's get going. Just give a bit of an intro on StyleGAN2. GAN, Generative Adversarial Network, consists basically of two networks. On one hand, there's the generator, and then there's the discriminator. The generator keeps generating new material, and the discriminator is the one judging whether this new material actually fits a given set of criteria or not. And this has proven very successful as an architecture to generate lots of things. You must have seen the explosion of better AI-generated art in recent years. And StyleGAN is an architecture from NVIDIA proposing to control basically different levels of details of the generated samples from coarser elements. From coarse elements like hairstyle or head shape to fine details like eye color or the presence of an accessory like a ribbon, say. So StyleGAN2 was a marked improvement in face generation, able to make coherent faces in a more convincing way. So we'll be using a pre-trained anime face StyleGAN2 model to generate our faces in this video. So how do we get started? Let's be sure we're here in colab.research.google.com and we can start a new notebook. Just give it a title, Anime Faces. And here we have these blocks where we can start typing in code. Before we do that, let's make sure that we have GPU enabled. So I went from runtime to runtime type, and I'm choosing the GPU because we will be running GPU intensive generation here. So let's create our first code block. We're going to bring in the StyleGAN2, zoom in a bit, by running a git clone command with an exclamation mark at the start. This is a bit of magic syntax in Colab that allows us to run this as if it was from the command line. So this is going to, in our instance of Colab running, it's going to clone the StyleGAN2 git repository. And this command will allow us to navigate to that place. We could run it right away by pressing this play button here. It's going to connect, initialize, and run it. So there we go, we've gotten it. Let's add the next code bit, and we will bring in TensorFlow, standard machine learning library, but we want to be using version 1 because that's the one compatible with StyleGAN2. So we can use this command to ensure that we're using version 1, whatever the latest 1 version is in Colab, which comes inbuilt with TensorFlow 1 and 2 at this point in 2021. Moving to 2022. Let's import a few things from here, and then let's bring in our pre-trained anime StyleGAN weights, which are just a Google Drive file, which you could host locally or you could host somewhere else. This is just a file that I'll link to in the video notes. We'll grab the model ID, which is the end part. So we'll just replace the beginning here with nothing and be left with the ID. grab the pickle file, .pkl, with whatever's the model ID, and we're going to download that file from Google Drive by using the Google Drive downloader, which we've marked as GDD, using the model ID as the file ID and the network pickle path over there. And basically all we need from there are these G's, which are the long-term average of the generator, which will yield a higher quality result than the spread snapshot. And then what we'll do is generate the initial vectors. Make sure we have a method to do that. We'll use NumPy, and these are Z vectors, which create the latent space for the model to start working from. And to quote, the latent space itself has no meaning. It's typically a 100-dimensional hypersphere, with each variable drawn from a Gaussian distribution with a mean of 0 and a standard deviation of 1. And basically, we're creating this array of random points from a given seed or set of seeds that then feed the model for the images to come out of. Though we will have a variable we can tweak to give a bit of control over what kind of images we'll get. And that will return these Z vectors, this method. And now we're going to create the methods for generating the images, import a few more elements, like so. We're going to save them down with pil.image and get some noise variables for a bit of stochastic variation with this command. And then we're going to use a trick you can find in the literature for a truncation psi value, which allows us to get more accurate results and also govern a bit how similar the images will be to each other. Will they be very, very similar, or will they be wilder, further away from each other, and just generally zanier, as we will see. So here we are generating images, actually using the model, using this truncation psi, which I'll link to, a bit more information about. And then just a combination method at the end here in this block of code, which will take the seeds that we pass to it and the truncation psi value, and then return the images that get generated from the seeds being run through this Z vector generation, along with the truncation psi being part of the image generation. So a lot of material there. This is the heavy lifting. This is actually running that data through the ready models and using this psi truncation tip. So once we've got these methods, we'll basically get these images. So we just need a method to actually send a seed value and send a psi value and then somehow render the image. And then we should actually start getting some results. Let's get rid of this and let's start creating that. So this one, we can just create one image to begin with. And let's say we grab a seed, random one, and we just indeed want one. So we want to pick it from 1 out of 10 million. And of course we could print the seed and then we'll have a reference if we want to use it again at some point. And we'll then set the psi variable for each run through. Let's try maybe 0.7. And basically the lower this value is, the more uniform, less diverse the images will be. The higher it is, the wider apart they will be, possibly veering into very, very interesting territory as well. Now let's generate the Z's with the method we defined above with this seed, and then generate images with these Z's, these randomly generated Z vectors, and this psi factor of 0.7. We could define a width and height of these images if we want to scale our picture, which we do want to. Just put it at 512. We could create a new canvas variable, which is basically a white background, why not, of the width and height we've given. And then we could take the image that we're getting. So the image could be the first thing we get back in our single element array, resize it by the tuple of the width and the height, and then use the anti-alias parameter for the resizing to see how it'll shrink. And then we can take the canvas and paste our image on it and return that canvas. So what happens then if we run this? Now we can run these blocks individually. We've run this one. Let's next run this one. We defined up here. TensorFlow 1 has been selected. It's downloading this file and taking some further steps. But it's only running this block of code, not rerunning this thing above, and not touching our blocks of code here below. And there we're done. Let's run this bit, which just imports NumPy, defines this method, and run this bit as well, importing all of these. We could choose, oh, don't have this quite right. Okay, so we need to make sure we have these snapshots of the generator and the discriminator being fed by what loads the network. That's going to come into the noise variables. So now this will work. We've got the noise variables, we've defined these methods, and they're available to us. Now we can run the create an image method. Let's see what happens. It's taking this random seed, printing it, and we get a totally new, freshly generated anime face. Let's run it again. Let's play around with the psi factor. What happens if we take a higher psi? Can we see the difference? We get a wilder face. Maybe 0.7 is good for now. Run that again. We get a different face, and again and again. Great, so we've got it working so far. Beautiful. Be nice to have maybe a set of these images, so maybe we'll create a method to print out a grid. That'll allow us to compare a bit. So we can start defining one. Maybe we'll want to pass in our images, select how many rows there will be, and scale our images as well. I'm copying this from somewhere else. So we'll get to scale the images, set the columns, the rows, create a new canvas as we did, and then for each image put it in its own place with a for loop. Resize it accordingly, paste it in its proper position, and then rewrite. So we might as well run this then. We can choose to run an image grid. So we'll add some stuff at the top, won't we? This generation part. So we might as well have size defined here. Size for the seed listing will be as large as whatever we pass through the create image grid. Psi should be passed through as well, I think. 0.7 is a good starting point. Let's make sure these are aligned. And then we don't need to pass images because we're getting them right here. So this top part here generates the images. Yes, let's give that a go. So could say rows 3, why not? Scale 0.5, 9 images all together with the default style. Let's try run this then. Not quite right. Here's the reason. This did not get typed properly. Let's try this. Okay, beautiful. We've got our grid of fresh new anime faces. Marvelous. Now maybe experimenting with psi will be a bit more interesting. So let's pass a psi value of 0.1. Rerun this script with these seeds that it randomly picked. And we get very, very similar faces with that low psi value. Same kind of hairstyle, same kind of head shape, similar eyes by and large, a little variation. Pretty neat nonetheless, but a clear difference. And what if we go the other way, go all the way to 2, we'll get something rather different. Very insane faces. Okay, maybe a bit too much. Let's pare that down to 1.2 for our last experiment of newly generated anime faces. Okay, interesting mixes. Kind of interesting, a bit different, a bit woozy. That's still quite okay. I do not know what's going on there. Fantastic. So that's just about the only customization we've got here. Let's revert that back to something a bit more typical. And that concludes this part of actually generating images. It doesn't take too long to get that running in Google Colab. But next, I'm figuring it would be great if we could generate a bunch of these and do something with them. So I was thinking creating a bit of a web app. There's a number of ways we could do that. We could maybe turn Colab into some kind of server and create a front-end web app where the user would send a request to Colab and it would then generate a face on the spot. But then I thought maybe that's a bit slow if Colab only is active part of the time, or you keep it active and it needs to rerun all of this stuff after a while of being idle to generate a face. The user response time might be just really bad. What we could do instead, as a simple example, is pre-generate a bunch of these new faces, save them somewhere, and run them, run a little front-end web app that then serves those images from wherever they are. And that's what I'll do for the rest of the video. We'll be saving these files down and then still in Colab creating a little front-end web app using Streamlit. So let's go. For saving the files, there's a very handy, easy integration with Google Drive, unsurprisingly with Google Colab. So let's use that. We can import the Drive method like that, and then just mount it in the Colab file structure in the content subfolder G drive. So what does that mean? If I click here, I'll be able to navigate the structure of the Google Colab instance I'm connected to, and here we see the content folder. So if I now run this, it should ask me to link the G drive. Yes, let's connect. And now we've got it mounted. So if I reopen content, we've got our Google Drive right here. So perfect. I can then maybe create a folder called Anime Faces where I'll end up saving these generated images. Beautiful. Okay, that bit is done. We've connected Colab to Google Drive. Let's create a method to actually generate and save images. Size, let's set some kind of default, and then folder needs to be something. We'll pass those in. Once more, we'll generate seeds. The size will be whatever size we're passing into the method. We'll print the seeds since we're in that habit. We'll set the psi maybe internally here. And generate z vectors from seeds, as we've seen before. Generate images. And then for index an image in the enumeration of images. We can use the index to give a number to the file that we're saving. So let's just use the save method on the image to put it in whatever folder we're passing through, plus file name could be face underscore, a bit of a clunky way to do it, index and .png in PNG format, of course. Remembering to close that bracket. And that's it, I think. Not to paste, PSI. Wonderful, and then we can run this. Okay, so let's try this one time. Let's try with 10, and let's be sure to set the folder properly. So we are putting it in content, G drive, my drive, anime faces. Okay, so let's make sure that we've got this / here as well. And then we'll get it in the right folder, I believe. Let's run the method. It's doing something. And here we go. Faces 0 to 9. Maybe we add +1 to the index. Future reference. Great, new faces. Saved down to our Google Drive. Let's run that a bit more. 256 new faces. That'll be enough for my friends. New anime ladies. Let's let that run. Great. So we'll have these files. Now we can take them, do whatever we like with them. Don't have to individually click through them and save them or anything. That's handy. Let's see if we can do the third element of the video, which is to create a little web app using Streamlit to display a page where you can click a button and get a new face and serve that externally on the web. So Streamlit is this very lightweight framework to get data scripts into web apps. We could use a lot of other things, but this just seemed like a simple option and something new for me to learn, so I'm going to use it here. And this is how we'll do it. Give it a go. Install it. So again, we'll have the exclamation mark to run a bash command, command line command. We will import Streamlit as just st, and from PIL import image to do our image processing, because we want to be pulling the images from the file now and serving them. Random is good, and glob to do the finding and reading of it. Okay, so let's load the photos. We could define a method, load images, create a bank image list array, and then read all those files, all those faces we see have arrived. Okay, so for file name in glob, let's give it the same location, content, G drive, my drive, anime faces, and anything that's a PNG file. They should all be that, but why not be sure? Let's just append that file name. Image list append file name. Great, and we'll return that image list. That's all we need to do there. Now, Streamlit by default is kind of stateless, because every time a variable changes or the user clicks the button, what it will do is run all of this code again. So it would load this list of images, and whilst we have 256 images, I wanted to make this a bit better and just kind of keep track of the ones we've already shown and only show ones that a user hasn't basically seen in that session. So let's add a little bit of state management, like so. So if we don't find it in state, so we're running this for the first time, we'll just run the load images method, and we'll store it in session state, basically like a dictionary with the, let's say, image list variable name. That will be our image list. And that's what we'll refer to otherwise. So we can modify our image list, and the next time this thing runs, we'll have that modified list available to us. Instead of initializing it every time. Now we can use a Streamlit method here called header to give the page a header that'll show whatever title we want to give our page. And then maybe we want to define a method to get a new face. So we'll pass the image list that we've drawn from here, and we will pick a new face randomly from our image list, and the image we have will be opened, and image list will, I want to remove that face from our list so that it doesn't get called again, and then we'll run a Streamlit method called sd.image to pass the image, give it a caption if we want. We do, and then that'll do it. Whenever we call the getFace method, we'll get a new image. Once we've done that 256 times, the array will be empty or so. So let's make a little thing here that if we're getting low, somebody's really clicking this thing and wanted to see all the faces, we can then just reload it if it gets low. We do want to remember to update the state list with this freshly refreshed one. So only if we're kind of running out of things on the image list will we reload the full list from the directory. Okay, so I think that should do it for that method. And then we need to have a button underneath. So let's get a new face. No help, but on click we will run getFace. No args. Nope. Okay, so that could work. Are we able to run it? Basically, Streamlit files want to be run on the background from the command line. So you can run this, at least to install the Streamlit library. That's critical. Okay, so we've got an error. I think we want to update the IPy kernel to be of at least this version. Just add another block of code. IPy kernel IDEC. Okay. Bit of troubleshooting. We may need to restart the runtime actually. To do that, I can do it from here. So let's restart runtime. Try once more. Okay, great. So that's running with no problem, but we're not seeing the results. What we can do is save this into a file. There's a few ways to do that. Maybe we want to do it, I think we want to do it here in StyleGAN. Create a new file. Let's call it web app. Open it and save our data there. So we can run a command to have Streamlit run this file in the background. So if we assume we're in the StyleGAN2 folder, we can run Streamlit run webapp.py and then ampersand chevron dead null. Let's see if that's found. But we still need to take one step, which is to open up that background process, what it might be serving on the local host, and have that, so something like this on the local host, and have it exposed to the wider world. And for that we can use a reverse proxy solution called Ngrok, and the Python wrapper for it is called Ngrok. So we can install that and give it a go. We'll need to authorize some things. Ngrok, but we want to run import it from Ngrok, import Ngrok, and create that public URL from wherever locally we're getting the web app, which with Streamlit should be 8501. So we'll say the public URL we're getting is this, and we'll just push out the public URL. Okay, opening a tunnel, and we get something. So it is tunneling public URL to this localhost value. It's only HTTP. So I'm going to visit this unsafe site, but nothing's running. We then want to make sure that the previous one operation isn't running, so we can kill all Ngroks. Let's remove this pip install from the web app. That might be confusing it because this exclamation point shouldn't work in a regular Python file. I think we can see from here that we're not in the right folder after all, after the runtime reset. There we go. Okay, so now let's assume that we're in the right place and run that again. Okay, Streamlit run, and then one more time, Ngrok. And something. And on we go. Okay, great. So now we're going to Ngrok, but we do need to authenticate. So let's sign up. Sign up with Google. And here's just auth token I will reset after this video is done. So we can just connect this account if we manage to run this. We can try putting it here, see if that works with the exclamation point. Actually, we might want to use the Ngrok method, so why not use it here? Ngrok.set auth token, I think it is, and we just grab the authorization token and put it in there. Maybe just as a separate piece. Don't want to be exposing auth tokens too much. So let's run that command, updating the authorization token. So now we've got that authorized link, a big angry red screen. Do we still have web apps running? Bit of touch and go here. Oh, and finally, here we have it. So we have a URL that I can send around with a header, as we said, infinite anime characters. And we click a new face and we get one of our 256 new faces. That's marvelous. A little bit of pain here on the second half, but we made it. Any tweaking we want to do? So in the web app, I removed the exclamation point from the start. I think we could have captions, right? You know, a random set of things, and then we might feed the caption with random choice from captions. Save it again, rerun our Streamlit web app in the background, use Ngrok to open that up. And as long as that's running, we should be able to run it again. Pardon me. Reload that page, and hey, we get little captions for our images as well. Our new friends gaining sentience bit by bit. Very, very lovely. Okay, so here we go. In not too long a time, we've ended up with this beast of an interactive Python notebook. What we did was use StyleGAN2, a pre-trained network fed with anime faces, using this code I've copied from elsewhere and will link to generate these random Z vectors to initialize these images, have this psi truncation trick running there. Then we looked at how to generate individual images with a seed, put it on a canvas and get it. Create a grid. You could animate these. You could maybe find ways to tweak individual variables so that you could have sliders of hair color perhaps, or eye color, or head shape. I think people have done that kind of stuff. We figured out how to connect Colab with Google Drive, saved down all our images, and then built a little web app on top with Streamlit, a little bit of touch and go, and then Ngrok at the end to create this URL, which I can now share with the world for a time at least, as long as this Colab notebook is active. So there you go. Let me know what you think. What are you doing in the space of cuteness, the space of machine learning generated art or faces, and what should we do next? Thanks for watching.